the fundamental theorem of algebra. Every non-zero polynomial p of x of degree n, so degree n means the highest power of x, so that means we can write our polynomial p of x as p of x equals an x to the power of n plus an minus 1 x to the power of n minus 1 plus so on and so forth all the way down to a2x squared plus a1x plus a0. And we also have that an does not equal 0, otherwise the x to the power of n would disappear and the polynomial wouldn't be of degree n. And then we can also have coefficients in C. So coefficients, as you should know, are the constant terms in front of the powers of x. So this time they are in C, so they can be complex numbers themselves. And just to be clear, also x can be a complex number. So x is a member of the complex numbers as well. So p of x is a polynomial of degree n with coefficients in C, and it accepts values from C. So it's a function from the complex numbers to the complex numbers. Okay, now for all of these kinds of polynomials, we are guaranteed that they can be uniquely factored as a product of a constant and n linear terms. So this an is the constant, and yes, it's the same an as this one here, and these are the n linear terms. So that means when you expand this thing here out, you should get this thing up here. The an's therefore have to be the same, but obviously the an minus 1, an minus 2, a2, a1, a0 are all going to be something about the numbers r1, r2, and rn. So the number an and all of the ri's can of course be any complex number. And as we mentioned, an is the coefficient of x to the power of n when this thing is expanded. So that's the fundamental theorem of algebra. Now, a few important details in the interpretation of this thing. So the polynomial p of x has coefficients in C. So that's these guys here. So an minus 1, a2, a1, a0. So these can be any complex numbers, including real numbers. For example, p of x equals x squared plus 1. Since all the coefficients are real numbers, and we know that the real numbers are a subset of the complex numbers, this theorem applies to this polynomial. And so that means we should be able to write it as, well, in this case, n is 2, and an has to be 1 because there's a 1 there. So we should be able to write this as x minus r1 times x minus r2. And what allows us to do this is this thing down here. The r1 and r2 can be complex numbers. So they can be any complex numbers that make this work. And in fact, we know that r1 and r2 have to be I and negative I. So x minus I, x plus I. But there's no real numbers r1 and r2 that will make this thing work. It only works if we can allow our ri values to be any complex number. We like that solves it. If there were real numbers r1 and r2, obviously we would have x squared plus 1 equals x minus r1 times x minus r2, and then if we set it equal to 0, that would imply that x equals r1 means r1 squared plus 1 equals 0, which is impossible for a real number because r1 squared needs to be greater than or equal to 0. So that's the fundamental theorem of algebra. It doesn't always work if we are looking for real roots, obviously, but if we allow our roots to be complex numbers, we are guaranteed to be able to write our polynomial p of x in this form. And as we can see, this is extremely convenient because if we set it equal to 0, then we immediately know that our values of x are r1, r2, all the way up to rn, and no others. Because if there was some other value that's not equal to r1, r2, or rn, then none of these linear factors would be 0, and then we would have a product of non-zero numbers multiplied together to get 0. One other thing, the r1, r2, all the way up to rn don't have to be distinct. Don't have to be distinct. For example, we could have p of x equals x minus r1 to the power of n. So that's counted as x minus r1, x minus r1, x minus r1. So multiplied together n times. So the theorem is not saying that there are n different solutions to the equation p of x equals 0. It's saying there is at least one solution. And we have some other theorems like the solution, complex number solutions come in complex conjugate pairs. So, for example, if x equals 2 plus I is a solution, then so is x equals 2 minus I. So details like that